Chapter 18, Example 2. Advances in medical care, such as prenatal ultrasound examination, now make it possible to determine a child's sex early in pregnancy. There is a fear that in some cultures, some parents may use this technology to select the sex of their children. A study from Punjab, India, reports that in 1993, in one hospital, 56.9% of the 550 births that year were boys. It is a medical fact that male babies are slightly more common than female babies. The study's authors report a baseline for this region of 51.7% male live births. So we want to test, is there an unusual amount of births, either below or above? So we're going to do a hypothesis test. We'll start with our null hypothesis, H null, which will be the probability equals the baseline amount, 0.517. We're always testing the baseline, not our sample. So the alternative, HA, will be the probability does not equal 0.517, because the question just says, is there a difference? It's not saying, are there more boys than we would expect? Those are different questions. Now we need to check our conditions, of course, just like always. So hypothesis, conditions, statistics, conclusion. The study was not random, but it is reasonable to assume the sample is representative of the babies born in the area. There's no reason to think only parents that are going to have boys go to one hospital or another. 500 births are less than 10% of all births in Punjab. I would expect 284.4 male births and 265.7 female births. Both at least 10. The conditions are met. I will use a normal model for a 1 proportion Z test. Okay, so now we're going to start calculate. First, our sample size is 550. The probability of getting a male from the population would be 0.517, assuming that it hasn't changed. And so our p hat, our sample value, is that 0.569. So now we calculate our standard deviation. Remember, this is standard deviation, not standard error, because this is from our population, not from the sample. The standard deviation of p equals the square root of 0.517 times 0.483, which is from the population, what we expect the true value to be, over 550. Again, we're not using that sample value until we calculate the z-score. So 0.0213 is what this comes out to be. We have a standard deviation of 0.0213. We have a normal model with a mean 0.517 and standard deviation 0.0213. So there's our normal model. We'll calculate the z-score in a second so you can see where I got that. But we just sketch as a two-tailed test again because we're saying not equal to 0.517. So we shade on both sides. We want to say what's the probability of that happening. So z equals 0.569. This is the sample proportion. minus 0.517, our population proportion, over 0.0213, the standard deviation. This gives us a z-score of 2.44. So we're doing a two-tailed test. So our probability, or our p-value, will equal 2 times the probability that our z-score is greater than 2.44, which equals 2 times 1 minus 0.9927, because when the z is greater than, we've got to subtract it from 1. And it comes out to be 0.0146. This is really low. In fact, that kind of standard value of 0.05 for sure. So, my p-value of 0.0146, always state your p-value in the conclusion, always, is low, and I will reject the null hypothesis. Always say either I will reject or I will fail to reject, whatever is appropriate for the problem. There is evidence to suggest the proportion of boys born in Punjab is not equal to the baseline. Always sum up your final conclusion there. Put it in context. Those are the three things you need to have in the conclusion. The p-value, I will reject or fail to reject, the hypothesis, and the conclusion in context. There's evidence to suggest the proportion of boys born in Punjab is not equal to the baseline, or there is not sufficient evidence.